Welcome to section 4.4. We're going to spend 2 days on undetermined coefficients. So the majority of it we're going to do today. And let's start off with a review of what we know about homogeneous second order linear differential equations. And then we'll talk about undetermined coefficients. So a review of what we've done over the past 3 sections. Characteristic equation for a y double prime plus by prime plus cy equals 0 is this quadratic equation, and depending on what the roots are, we have different solutions. So we've got the 3 cases are 2 real roots, repeat real, or complex roots. So we're going to use this today. We're going to use this to find yc, which is the solution of the associated homogeneous equation. So let me remind you of solution structure. Suppose you're trying to solve a non-homogeneous differential equation. So that means over here, instead of equaling 0, you have equaling f of t. The general solution of the non-homogeneous is going to be any particular solution of the homogeneous, yp, plus yc, which is the general solution of the associated homogeneous differential equation. So this is the dE equals 0. And so this, finding yc, this is sections 4.1 through 4.3. That's what we've been doing so far. We've only been doing homogeneous, so we haven't been calling it yc, we've just been calling it y. But today we're going to start calling it yc. And in order to find y, we're going to add yp to yc. So we haven't talked yet about how to find yp. That's what we're going to do today. So this is today, finding yp. All right, so here's just a simple example. Given that yp is negative t, so given that that's a solution of this non-homogeneous differential equation, find the general solution. All right, so the general solution will be yc plus yp. So we need yc, which is the general solution of y double prime minus y equals 0. That's the associated homogeneous differential equation. So the characteristic equation of that is r squared minus 1 equals 0, which factors as r plus 1, r minus 1. So we have 2 real roots, r equal plus or minus 1. And so yc is c1 e to the t plus c2 e to the negative t. And so the general solution of the non-homogeneous, let me erase that, general solution is going to be y equal to yp, which is negative t, plus yc, which is c1 e to the t plus c2 e to the negative t. So this is my yp, and this is my yc. When you add those two together, you get the general solution of the non-homogeneous. And in this case, yp was given to us, but today we're going to see how to find it. We already know how to find yc. Okay, so the method of undetermined coefficients. First of all, it can only be used on differential equations with constant coefficients, a, b, c. Second of all, the non-homogeneous part, the f of t, the driving function, can only be a certain type of function. It has to come from this list: a polynomial, sine or cosine, any exponential, or a finite sum or product of those 3. Okay, so let's look at some differential equations and determine which ones we could use undetermined coefficients on. So the first one is a no, because this function over here is not in the list of approved functions. Can't have a natural log. You can't have any log. Second one, it looks good so far because we have a polynomial over here, but if you look carefully, there's a variable in the coefficient, so that's no. The third one doesn't look good because it looks like a quotient, not a product. So you're only allowed to have products. But actually, this one's a yes because you can write t squared plus 1 over e to the t as t squared plus 1 times e to the negative t, and that's an exponential. So the product of an exponential times a polynomial is allowed, and there are constant coefficients. So that one's good. The next one, yes, absolutely. No problems there. Next one over, no, tangent's not allowed. Tangent is a quotient of sine and cosine, but that's not allowed. Next one, again, no. We've got constant coefficients, but we can't have a t to the negative 1. We can't have a quotient of polynomials. Okay, so how to use UC. So the first thing you're going to do, there's 3 steps. Find a complementary solution YC of the associated homogeneous. So that's using the rules at the top of the page here. You're going to use these rules to find YC. Then you're going to use the table here to find the trial form of YP. And the reason why I say trial is you're going to have to check your YP against YC. If there are any repeats or duplicates, same thing, you're going to have to multiply by t so that you won't have any duplicates. I'll explain that in a minute. Then you're going to find YP prime, YP double prime, plug all of those into the original differential equation and solve for the coefficients. Okay, so you can see here in my table of trial solutions, you're going to match up your trial YP basically with the type of function you're given. If you're given a polynomial, your YP is going to be a polynomial. If you're given sine, your YP is going to have both sine and cosine. You have to account for both. We'll go through some examples in a minute. In fact, here's some examples, and I've got some more on the very last page for you. But if your f of t is a polynomial, then you need to replace that with a trial YP of a generic polynomial. So if there are missing terms here, you still need to have all the terms in your trial YP. Next one is a polynomial times an exponential. So a polynomial times an exponential is going to have YP, a polynomial times that same exponential. So if this is a 4, this is going to be a 4. And then your t squared gets replaced with the generic quadratic polynomial. If you have sine 2t, you're going to need, and the 7's irrelevant, you're going to need a constant times sine of 2t plus a constant times cosine of 2t, because you might have sine and cosine in your answer. If this had been 7 cos 2t, you would use the exact same trial YP. You'd need a sine and a cosine. If you have a polynomial times a cosine, you're going to need a generic linear polynomial, at plus b, times a cosine, and then a generic linear polynomial times sine. One common mistake is to try and write that like this, and you cannot. So you cannot write at plus b and then times c cos 3t plus d sine 3t. You have to write it in the way I've given it to you. Okay, what are duplicates or repeats? Suppose your YC looks like this. You got 2 exponentials, and your trial YP is at plus b times e to the 2t. If you're looking for repeats, when you distribute this in your head, b e to the 2t is a constant times e to the 2t. That's a repeat with this guy. And so that would be bad. You'd have to multiply all of this by t to avoid the repeat. You'd have to do your new YP would be at squared plus bt e to the 2t. That has no repeats. If your YC is this here with sine and cosine, 3t, 3t, and your trial YP were this, then you would also have repeats because when you distribute, you'd have a constant times sine of 3t, that's a repeat here, And you'd also have a constant times cos 3t. That would be a repeat here. So you'd have to multiply all of this by t and all of this by t. All right, and finally, this last example has no duplicates because even when I distribute, I have b e to the t, but this is e to the 2t and that's e to the negative t. The exponentials are different. All right, so hopefully this will become more clear as we do examples. I know it probably seems a little bit overwhelming right now. So I'm going to take us through a full solution for each of the three types of allowed functions, a polynomial, an exponential, and one with sine and cosine. So let's start with a polynomial. So we want to find a particular solution for this differential equation. We start by finding YC. So we're going to solve the associated homogeneous DE. So I wrote down the characteristic equation, I factored it, I saw the roots were r equal -1 and 2. And so my YC is going to be C1 e to the 2t plus C2 e to the -t. The order doesn't matter. Then we go and write down our trial YP. So here's my f of t. It's 4t squared. So my table would tell me that if I have a polynomial for f of t, I want to replace that with a generic polynomial, in this case quadratic, for yp. At squared plus bt plus c. And I look for duplicates. So I'm checking against this guy up here, looking to see if I have any duplicates. No, I don't. So there are none. So this is going to be my final YP. And I strongly suggest if you have to multiply by t, you cross out your trial YP when you write down your final so that at the end, when you go back and plug in ABC, you don't go back to the wrong function. I've done that before. Okay, now we find YP prime and YP double prime. So just take the derivative, 2AT plus B, and then take the derivative again, 2A. Now we go back to the very initial given differential equation, and we plug all this information in. So wherever we see a y double prime, we're going to put in yp double prime. And I did this because it's a lot of algebra, and it would take forever if you just watch me do each step. So I've sped us along here. I put in yp double prime, and then I subtracted yp prime, which is 2at plus b. And then I'm supposed to subtract 2y. Y is at squared plus bt plus c. And I set that equal to 4t squared. Okay, so that's the beginning step. Then I combine coefficients. So I look to see what's the coefficient of t squared. It's going to be -2a. Then I combine the coefficient of t. I've got a -2a, and then I've got a -2b. So that's my coefficient of t. And then I look for the constant coefficient, and I wrote that down. It's in green. Now I've written 4t squared as 4t squared plus 0t plus 0, because now we're going to do what's called equating coefficients. If you have two polynomials, this is the red box, if you have two polynomials that are equal, that means the coefficients of, in this case quadratic polynomials, the coefficients of the quadratic term are equal. So if you have at squared here and dt squared there, a must be d. The coefficient of t has to be equal to the coefficient of t. So b is e, and then the constants are equal. C is f. So that's why I combined coefficients on the left, and then I wrote it like this. So now I'm going to write down three equations. I know that -2a must be 4, and I've color-coded it, so the reds are equal, the blues are equal, and the greens are equal. -2a minus 2b is 0, and 2a minus b minus 2c is also 0. So 3 equations, 3 unknowns. I don't need linear algebra to solve this system. It's pretty straightforward. I just start at the top. A must be -2. And then I plug that into the second equation, and I'm going to see that b is 2. And then in the third equation, I'd have negative 4 minus 2 is 2c. So c is going to be negative 3. So I know A, B, C. So I go back to my YP. Now I have a particular solution. YP is negative 2t squared plus 2t minus 3. I did it. All right. Now, we were only asked for a particular solution in this case, but if we had been asked for the general solution, I'll write that down to the problem, then the general solution would be yp plus yc. So that would have been negative 2t squared plus 2t minus 3. And then yc was c1 e to the, I've forgotten, 2t plus c2 e to the negative t. There's my general solution. Okay. So next one, we're going to do an exponential. We're also asked to find both a particular solution and the general solution. So step 1, solve the associated homogeneous differential equation. The homogeneous part is the exact same as it was in our last example, so I don't need to redo things. I'm just going to write down yc. In this case, I put e to the negative t first and then e to the 2t second. That's okay. It's the same function. So step 1 is done. Step 2, I write down my trial yp. So here's my f of t, which is a constant times e to the negative t. So I go to my table and I see that if I have a constant times an exponential, I want to replace that. Write down trial here. Trial yp is going to be a constant, a e to the negative t. Okay, so then I look at my yc and I say, are there any repeats? Yes. I have a constant times e to the negative t there. So there's a repeat or a duplicate. So I have to multiply by t. I want the lowest power of t that's going to eliminate duplicates. So my final yp is at e to the negative t. I'm going to cross this out so that at the end I don't go up there and plug in a to that function by mistake. Now when I say the smallest power of t that will eliminate duplicates, suppose that yc had been c1 e to the negative t plus c2t e to the negative t. Then for my trial yp, ae to the negative t, there would be a repeat. But if I multiplied by t, I'd still have a repeat, right? Because then I'd have a repeat with this term. So the smallest power of t I could multiply by in that case would be t squared. And I'd have to do that to eliminate repeats. By the way, if you don't eliminate repeats, then when you go to step 3 where you plug in, what's going to happen is anything that's a solution of the homogeneous is going to get crushed on the left, and you won't end up with any coefficients to solve. So it's an important thing to check for repeats. All right, so I think I spelled final wrong there. All right, there we go, final. So I've got my final yp. Now I need yp prime and yp double prime. So I need to use the product rule. Yp prime is going to be a e to the negative t and then minus a t e to the negative t. And yp double prime is negative a e to the negative t minus, I need the product rule again, a e to the negative t and then minus at e to the negative t. And so if I clean that up, I've got negative 2 a e to the negative t, and then minus minus is a plus a t e to the negative t. Okay, step 3, plug in. And I've done some of this for us. Go to the original differential equation, and y double prime gets replaced with yp double prime, y prime gets replaced with yp prime, and y gets replaced with our final yp. So I did that, and now what I want to do is combine like terms. So I want to combine the coefficients of e to the negative t and te to the negative t. However, when I look at this, I say, okay, I've got at e to the negative t, and then I have another one of them because minus minus is a plus, so I have 2 at e to the negative t, but then I'm going to subtract 2 of them. So this guy's going to kill this guy's going to kill this guy, and I'm only going to end up with minus a e to the negative t minus another one would be minus 3 a e to the negative t. So the left-hand side is going to simplify to that, and that's 4 e to the negative t. Now I can, again, equate coefficients. If negative 3a e to the negative t is 4e to the negative t, that tells me that negative 3a must be 4. Because the coefficient of e to the negative t on this side has to be equal to the coefficient of e to the negative t on the other side. So now a is negative 4/3. Okay, so my yp, go back up and check, make sure you don't plug into the wrong function. Here's my yp, because remember I had to multiply by t. So my yp is negative 4/3 t e to the negative t. That's a particular solution. And my general solution, I just take yp and add it to yc. So I get y equals negative 4/3 t e to the negative t plus c1 e to the negative t plus c2 e to the 2t. You're actually, I don't think you're going to be asked for the general solution until you get to the next section. In this section, they're going to ask you just for a particular solution, but you may as well learn how to do both right now. There's no reason to wait. Okay, so last one, sine and cosine. So we've got, in this case, I gave us a different homogeneous part. So we're going to solve the associated homogeneous equation, which I already did for us. We've got a quadratic that factors with 2 roots, negative 2 and 1. So here's my YC. Okay, that's an easy step. Step 2. This is my f of t. So if I go to my table for sine t, in the table I think it's beta t, your beta is 1. Sine t, you're going to need a constant times sine t. You're going to need a constant times cosine plus a constant times sine. The order doesn't matter. You could put a sine t plus b cosine t. That would be fine. The only thing that's important is once you make your labels, stick with them. So at the end, you go back and put your a in front of cos, your b in front of sine. If you switch the labels, you'll switch the function when you're done. Okay, so yp prime. Negative a sine t plus b cos t, yp double prime, negative a cos t minus b sine t. Oh, sorry, forgot to check for repeats. On step 2, we write down our yp and then we go repeats or duplicates, question mark, and then there weren't any. That's why I glossed over that, but I'm sorry, I should have told you I was checking. So I'm looking against these guys. I see there's no repeats between these functions and these functions. So that was my final yp. My trial was equal to my final. Step 3, I want to plug all that information into the original differential equation. Okay, and I started this out. So these are pretty much take a while to do, and it's easy to make a mistake. So make sure you write down your work pretty carefully as you're going. At this point, once you plug in, so here's my y double prime, and then this is my 3y prime, and then this is 2y equals sine t. You want to combine the coefficients of sine and cosine on the left. So if we go through cosine, we get, okay, there's a negative a cos, and then there's a 3b cos, and then there's a 2a. So that gives me altogether a plus 3b times cosine. And you can go through, collect the coefficients of sine, all right? And then on the right, I've got sine. I want to think of sine as 1 times sine and 0 plus 0 times cosine. Because again, I'm going to equate coefficients. The coefficient of cosine on the left will be equal to the coefficient of cosine on the right. I said left and right, but I pointed to different directions. So sorry about that. But you get the idea. The coefficient of cosine is going to be equal on each side. So the coefficient of sine on the left here has to be equal to the coefficient of sine on the right. So this is going to give me two equations. A plus 3b should be 0, and negative 3a plus b should be 1. Two equations, two unknowns. I'm going to do the elimination method. I'm going to multiply the top equation by 3 and add it to the second equation to get 10b is 1. So now I know that b is a 10th. And then a, plug that into the first equation, and I'm going to get a is negative 3/10. So my yp, here's where you want to go back and make sure you're putting, like, so a is the coefficient of, for me, cosine. So I want to put the negative 3/10 in front of the cosine and the positive 1/10 in front of the sine. Okay, so there's my yp, and then I go back again to the top and I read what was asked for, because at this point I've forgotten, did I want the particular solution or did I want the general solution, or did I want both? So reading, find a particular solution. So that's all we had to do is find yp. No big deal if I had wanted the general solution, it would just be more writing. I would take yp and add it to yc. Okay, so there's an example of each three. They're not difficult, but you need to be careful and methodical and write down your work. It's easy to miss a minus sign on these sine cosine ones. All right, last thing we're going to do is a little glimpse of the next section. Suppose your yp, suppose your f has two parts, like a polynomial and an exponential, where it's a sum, not a product. Then there's nothing in the table that would give you a trial yp for this function f. So the way to do that is to think of it as an f1, which would be a polynomial, and an f2, which is an exponential. All right, and then your trial yp will be yp1, which is your yp for the f1, yp1 plus yp2, which is your trial yp for the f2. So for a trial yp for a generic quadratic, for f1, which is a quadratic, we want a generic quadratic. So we want a t squared plus bt plus c. So there's our yp1. Now we're going to add on yp2, which would be the trial yp for this exponential, which is a constant times e to the 3t. So I want a constant d e to the 3t. Now, a common mistake is, since this is yp1 plus yp2, is to start from the beginning and say, oh, I'm going to use a again. You can't do that. A is being used, so you can't, it's not the same a, right? So call it something different. Call it d. So I've got yp1 plus yp2. Then I check for repeats. And I've already written down I've given us the fact that YC is this function here. So when I look at YP1, I don't see any repeats. When I look at YP2, I see a repeat. I see constant times e to the 3t. Now, if I multiply by t, I'll still have a repeat because I have a c2 t e to the 3t. So I have to multiply this guy by t squared. Now, the important thing here is when you have the form yp1 and yp2, you're only going to multiply the offending yp by powers of t. If, in this case, yp1 was not offending, so don't tamper with this. Don't multiply it by t squared. Just leave it alone. So this one's good. This one we need to fix. So our final yp would be our old yp1, because that was fine. And then our yp2, we're going to multiply by t squared, so dt squared e to the 3t. So that would be our final. Okay, so your homework for this section, in terms of the homework you have to upload on your lecture notes, isn't that bad. I've just given you 4 problems, and you're going to write down, and each one is the same homogeneous part, and I've given you the solution to the associated homogeneous. It's C1 cos t plus C2 sine t. So in each case, you're going to write down the trial yp for the function f. The only change in each case is your f. So write down the trial yp, check for repeats, and then write down your final, I'm having trouble with the word final today, final yp. And if you don't have to multiply by any powers of t, you can just write final yp is same, all right? Otherwise, multiply it by whatever power of t you need to. So in each case, you'll just be writing down trial and final, trial and final. You won't have to do any computations. You're not actually finding the coefficients. I'm just asking you to write down the appropriate form of yp. All right, that's the end of this section.